Hello, good evening everyone. So today we are here for our second last live session, the 11th one, and as you all know, we are discussing our NPTEL course assignment question, which is Ultrafast Laser Spectroscopy, taken by Professor Anindya Datta from IIT Bombay, and I am Shruti, the one of the TAs of the course. So today we will be discussing assignment number 10th, and the next two assignment, which is 11th and 12th, we will take it together next week. So let's wait 5 minutes and then we can start our discussion.
मोटी ले जाएंगे में जमराज लंदन से
So let's start now. We have already covered a lot of topic in the course, and we have almost like the 12th week content has already been released, and we are approaching the end of the course, and the exams are also near. So let's finish it off quickly. So weekly assignment 10th. The first question states 7-aza-indole dimers are a good model for amino acid protein, DNA base pair, cholesterol in lipid membranes, histone in nucleosomes. So let's first see what are 7-aza-indole dimers. So this is one 6-membered ring and one 5-membered ring is attached to it. The indole ring is attached to it, and here is a double bond. So this is one molecule, and since it is dimer, we will have another one like here. I will draw it with the black color. So here we will have the N. Okay, so this here is H, and since it is a dimer, there should be some bond between them, some connection between them, and they are connected by these hydrogen bonds. Okay, so this one is the covalent bond, with 5-membered ring, and this one is the hydrogen bond to 6-membered rings. Okay, so this kind of thing is found in DNA base pair. So it is a model system for DNA base pair. So in DNA we have ATGC pairing, base pairing. So this is similar to that. A double bond, A not double bond, it is 2 hydrogen bonds, and G is connected to C, guanine is connected to cysteine via 3 hydrogen bonds. But here the thing is, in base pairing, these are two different molecules A and T, G and C. Two different molecules, but here we are using the same molecule. As it is a dimer, so we are using the same molecule. So this is the thing, and here we will have there is a here it's a C2 axis passing through the plane here, and C2. How do I point C2? And then this is the sigma plane, the plane in which the molecule is there, the plane of the screen. So this is a sigma plane which is perpendicular to the axis C2 axis. So it is a sigma H plane. So this molecule has a C2 axis plus sigma H. So it has C2H symmetry. So that's it. The question asked about that these dimers are good model for amino acids in protein. No, they are good models for DNA base pairs. The answer is DNA base pairs. Okay, let's move to the next question. The next question is, in the femtosecond fluorescence traces of 7-azindole dimers, there is a fast decay at longer emission wavelength. There is a rise at longer emission wavelength. The fast component of decay is single exponential, or the fast component of decay is double exponential. Let's see how the decay is. So let's see the time resolved femtosecond. Time resolved fluorescence of 7AI dimer. So in 7AI dimer, what happens is the proton transfer, double proton transfer. So first, as I had drawn, let me copy the molecule. I'm not able to select this. I'll have to draw again. So we have and here is the membered ring. And one H is covalently bond, the other will come from here. So this one is the hydrogen bond, and this one will be the another 5-membered ring it will be. So let's draw the 6-membered ring here. NH, this is the 5-membered ring. Yes. And we have one double bond here and one here. And there is another hydrogen bonding here. So this H is transferred to here and this H is transferred to here. So we have now the bonding changes, and in the 5-membered ring we get covalent bonding, and in the 6-membered ring we get hydrogen bonding. So the 5-membered ring here is the covalent bonding. Now let me show the exchanged protons by green. And this will have the hydrogen bonding, okay. So after the double proton transfer, this 5-membered here, initially the 5-membered ring was having only hydrogen bonding, this part. Now here it is covalent, and the 6-membered ring, which initially used to had this, here was the covalent, here it became hydrogen. The covalent bonding became hydrogen bonding. So this is what happens after double proton transfer. So when the time resolved fluorescence decay was taken for this molecule at blue wavelength and the red side of the wavelength, we got plots like this. So here is the decay, and here is the counts or FL intensity. Now at the red edge, and here I will draw the blue edge. I am drawing only one wavelength. So what happened at the red edge, there was a rise. Like this. And at the blue edge, there was a decay. So this is at 380 nanometer, and this was at red edge around 620 nanometer. So what happens? We see a rise here, and a decay here. Okay. So the question is asking about in the femtosecond fluorescence traces, the decay, there is a fast decay at longer wavelengths. So this is the longer emission wavelength, but here we did not see any decay. Sorry, do not see any fast decay. So let me write over here. No fast decay here. There is a rise at the longer emission wavelength. Yes, it is correct. We have a rise at the longer emission wavelength. This is the rise. This is the rise. So at the longer emission wavelength, which is the red side, 620 nanometer, we see a rise. So this second statement is correct, that there is a rise. Third statement is, it's a multiple select question. Square check boxes are given. So the third statement says the fast component of decay is single exponential. So here we have the fast component, here we have the decay, and the fast component I have not drawn properly, but the fast component is double exponential. Okay, so in the blue end, the fast decay is strong, from the locally excited state. I'll write it in short LS. And in the red edge which we saw, and the red edge is for the proton transfer dimeric form, which is formed in the excited state. Okay, so this is and in between I have not drawn. So in between, at around 400, we see a rise and a decay. With this color. So this is at around 450 nanometer. It has a rise and decay. Okay, so this one is so around 450 nanometer. There is both fast decay, which is followed by a rise. So at this wavelength, in the mid wavelength, there is both a decay and then a rise. So the locally excited state, it also makes a contribution to the fluorescence emission, and then there is a rise which is due to the proton transfer state. Contribution to fluorescence emission at this wavelength. And we see a decay. Okay, so to answer this question, it was there is a rise at the longer emission wavelength, which is true, and the fast component of decay is single exponential. Now the fast component of decay is double exponential. Okay, so this is the second question, that when the time resolved fluorescence decay is taken at the red edge and the blue edge, at the red edge we see a rise in the decay, rise in the fluorescence decay, and in the blue edge we see a faster decay. That's all, and let's move to the third question. Third question is that fluorescence of 7-azindole dimers reveals the existence of ultrafast, fast, and slow component, and contribution to the absorption spectra is given by the ultrafast and the fast, or the fast and slow component, or the ultrafast and slow component, or all three. So let's see. From the time resolved fluorescence spectra, that the time resolved fluorescence intensity is given by So if this is happening, P1 is changing to P2 in time tau T1, tau T2, and then it is changing to P3 and then and so on. So this is given by P3 P3T. So from the fitting, we get this tau 1, tau 2, tau 3. And here the K1, K2, K3 are the fluorescence spectrum. In the wavelength space. That is the normal fluorescence spectrum. And there is a term called oscillator strength, which shows how strong is the transition. Okay. So when these things were calculated for the 7-azinyl dimer, their properties came out to be I'll make a table here. Component. So first was the ultrafast part, then the fast component, and then the slow component. So ultrafast component was 0.2 picosecond. Fast component was 1.1 picosecond, and the slow component was 3 nanosecond. Okay, so So the ultrafast component, for this the origin was the dimeric S2 state, and its lambda max was at 330 with fluorescence lifetime 0.2 picosecond and radiative lifetime 13 nanosecond, quantum yield very less, and oscillator strength 0.13. For the fast component, it was dimeric S1. Its radiative lifetime more, quantum yield more, but the oscillator strength was less. And the slowest component, it was originated due to the tautomeric form. Its lifetime was in picosecond 3220 picosecond, radiative lifetime 160 nanosecond, 2.0 into 10 to the power minus 2, quantum yield the highest, and the oscillator strength was 0.023. So this was the data. Now let's see the oscillator strength thing. So the oscillator strength which they got, actually oscillator strength is calculated from the absorbance spectra. So from the absorbance which they got, oscillator strength was about 0.16. Now for ultrafast, we had 0.13, for fast 0.048, and for slow 0.023. So when you sum these two, the ultrafast and the fast, it will come approximately at 0.16. So the absorbance band consists of the fast and the ultrafast component. This means that the absorbance band consists of the transitions to two states. So that those two states were dimeric S2, from dimeric S2 and S1. So this means that the ultrafast and fast components The ultrafast and the fast component together make some sort of ensemble, twofold excited state ensemble to which the excitation is taking place. So to answer this question, the question was contribution to the absorption spectra is made by which components? So the answer is clear now because from the oscillator strength which we get from the absorbance is 0.16, and from the fluorescence data, if we sum the ultrafast component and the fast component oscillator strength, we get roughly around 0.16. So which means that only the fast and the ultrafast components are contributing to the absorption spectra. So the answer should be the ultrafast and the fast component 1 and 2. Okay. So I hope the question is clear now. Let's see the next question. Fluorescence depolarization of a 7-azindole dimer with a time constant of 12 picosecond is ascribed to excited state proton transfer, rotation of the molecule, crossover from the locally excited state to another state without proton transfer, or twisted intramolecular charge transfer. So, the fluorescence depolarization, that is the change in the fluorescence anisotropy. So the data which was discussed in the course was regarding this question was anisotropy change of fluorescence from 7-azindole dimer. So the excitation was done at 270 nanometer, which is due to the benzenoid band. The benzene group is there, and the sample was 10 to the power minus 2 molar in hexane. So the time constant, so it was done at two excitation, the red edge and the blue edge. So for red edge, so here the red edge 500 nanometer and the blue edge okay. So the anisotropy pen is not writing. Now it's fine. So I'll just draw the spectra how it came. So it had an ultrafast component and then this part. So this part was the ultrafast component. And in the red edge, it was like this. So this was 12 picosecond. At 380 nanometer, we saw at 380 nanometer, or blue uh, in the blue edge, we saw there was a fast decay in the emission spectra. We saw that in the second question. The fast and in the anisotropy we just now saw that there is an ultrafast component. So this cannot be due to rotation. Okay, and in the red edge, the 500 nanometer, there was a rise in the fluorescence fluorescence spectrum. The rise followed by a very slow decay. Due to tautomer. And in the red edge, we see that the anisotropy evolution is also slower, around 12 picosecond. So this slower decay can be assigned to the rotation of the molecule. The depolarization takes place due to rotation mainly. Rotation cannot take place in the ultrafast time scale. So the slower time scale was assigned to the rotation. So answer this question. The question is that with the time constant of 12 picosecond is ascribed to excited state proton transfer, rotation, crossover from the locally excited state to another state without proton transfer, and twisted intramolecular charge transfer. So the answer is B, rotation from the rotation of the molecule. Let's see the next question. And the next question is again about the faster time scale 0.2 picosecond, and that was assigned to the crossover of the locally excited state to another state without proton transfer. So let's see how. So this one is the 0.2 picosecond component is taken for S2 to S1 relaxation. S2 to S1 electronic relaxation. So it is just a relaxation process without the proton transfer. Okay. And in the next step, the proton transfer happens, which is 1.1 picosecond component. And the proton transfer is concerted, not stepwise. So the proton transfer will happen. The hydrogen, the covalent bond will go with the 6-membered ring, and the hydrogen bond will come to the 5-membered. this is the covalent bond, and this is the hydrogen bond with the 6-membered ring. Sorry, hydrogen bond with the 5-membered. This is the 5 hydrogen bond with the 5 and covalent bond with 6. Here we had covalent with 5 and hydrogen with 6. So after proton transfer, this got reversed. So the depolarization of the ultrafast component 0.2 picosecond, fluorescence depolarization occurring in the ultrafast time scale, which is 0.2 picosecond. It was assigned to this crossover from the S2 to S1 state, which is happening in this ultrafast time scale, and not the proton transfer or the rotation. Okay, so this answers the 5th question, that this was due to the ultrafast component was due to this crossover. So let me write a bit here about this thing happening, that when we excite the the molecule, so the two states singlet, there are two states, one LA and the one LB states. Here this, the upper one is the one LB and the down one is the one LA state, and this is the ground state S0. So this state has a polarization like this, and this state has a polarization like this. So they are almost perpendicular. So when we excite, the LB state gets excited, which is S2. It gets excited, and then it gets which gets transformed to this one LA state, which is the S1 state. via vibrational cooling or vibrational relaxation in 0.2 picoseconds. So this time is related with this transition from 1LB to 1LA, and this is the excitation, and then emission comes from. So after this double proton transfer happens, from the relaxed S1 state. So from electronically relaxed S1 state, or this 1LA state, of the dimer. And also Takuchi and Tahara, they claimed that the double proton transfer is concerted. That is, both the protons get transferred at once. Get transferred at once and not one at a time in 1.1 picosecond. So 1.1 picosecond component is associated with the proton transfer both at once. Both take 1.1 picosecond to get transferred, and in the 0.2 picosecond it is the relaxation time from 1LB state to 1LA state. Okay, so the answer should be now clear that it is not due to the proton transfer. There is no charge transfer here, not due to the rotation. The rotation was uh, for the higher time scale, 0.12 picosecond. In the faster time scale, it is the crossover from the locally excited state to another state. Locally excited state is 1LB to another state, which is 1LA, or the S1, without the proton transfer. So this is important, that this is the crossover from S2 to S1 state without the proton being transferred. So I hope the question is now clear, and the answer is clear. So let's move to the next one. The sixth question is, the excitation of 7-azindole dimer in the red edge of its absorption spectrum yields. So, excitation at the red edge. So all the answers are related with anisotropy. So let's read out the options. First is, the excitation at the red edge of the absorption yields double exponential decay for fluorescence intensity, but single exponential for absorption. So it has to do with both fluorescence intensity decay and the anisotropy decay. So single exponential for fluorescence intensity, but double exponential for anisotropy. Double exponential for fluorescence intensity as well as anisotropy. Single exponential for fluorescence intensity as well as anisotropy. So when we excite it at the red edge, so since the red edge, it will just get excited to S1 state. So let's see if this is the if this comes due to excitation to S2 and this comes from S1. So if we excite at the red edge here, then the S2 to S1 convergence should not happen here at lambda 3. For example, here is in between. So at this wavelength, S2 doesn't get excited. And the decay, the ultra-fast component of the decay, which was coming from the crossover from S2 to S1 state, this should not be visible because here only S1 is getting excited. There is no S2 excitation. So there should be no vibrational relaxation. 0.2 picosecond component should not be seen or observed. Okay, and there should be only one component which is due to the proton transfer, right? So let me draw in the new page. Picosecond, and this is fluorescence intensity decay. So at the red edge here, it came as single exponential. So it got fed to a straight line. So this was at 313 nanometer and it gave a single exponential with lifetime 1.1 picosecond. So you see there is no 0.2 picosecond component present over here. But at the blue edge, this is not asked in the question, but at the blue edge, it was like this. So here we have two components. It doesn't get fitted to a straight line. So at the blue edge, both S1 is also getting, S2 is also getting excited. So there is S2 to S1 conversion. And this one is bi-exponential. So it has 0.2 picosecond component and the 1.1 picosecond component for the proton transfer. So this is the case for fluorescence intensity. The semi-log plot this is a semi-log plot. So we see in the red edge, this is the red edge. So in the red edge, the fluorescence intensity is single exponential. So single exponential for the fluorescence. So it could be either option B or D according to the fluorescence intensity being single exponential. But let's see how is the anisotropy decay in the red edge. So here is the delay in the picosecond, and here is the anisotropy. So for the red edge, it was like this at 313 nanometer, that is the red edge, which is single exponential. And this is again a semi-log plot. And for the blue edge, so the longer time scales are same, but there is a difference in the shorter time scales. So this is the blue edge. To 70 nanometer, and this component was 0.2 picosecond component, and this faster component is 12 picosecond component, which is due to the rotation. Is due to the diffusion. So red edge came as single exponential. When excited at 313 nanometer, I'm writing the same thing which I told just now. Anisotropy is almost single exponential. And at 270, which is the blue edge, there is ultrafast component in the initial times. Zero 0.2 picosecond. So from this they confirmed that, okay, so to answer this question, the answer is now clear that it is single exponential for both decay of the fluorescence intensity and decay of anisotropy. The answer is B. Now from these experiments they concluded that one state makes way for the other in 0.2 picosecond. And this is associated with decay of population, that is the fluorescence decay, and also with change in the direction of polarization or the dipole moment, because the two states have dipole moment oriented perpendicular to each other. So that's why there is a change in the anisotropy. And the other conclusion was, in the long run, both lines are parallel. Both lines parallel means these two lines. In the longer time scale, these two lines are parallel, which is due to the rotation. But in short time excited state process is happening. And this excited state process happening, this can be seen only in the blue edge. Only at higher excitation, that is the blue edge. Higher excitation energy. Okay, so with 270 nanometer, we excite S2 state, and with whatever 313 nanometer, we excite S1 state directly. So this was the conclusion they got from these two decay. Okay, so this was question 6. Let's move to question 7. We have a lot of questions left. Question 7 says that the Kasha's rule is usually obeyed in most fluorophores because S2 state is completely non-emissive. It is usually not populated by direct electronic excitation, is very short-lived, and so its emission is minuscule contribution to the steady state intensity, usually undergoes rapid intersystem crossing. Kasha's rule is usually obeyed in most fluorophores because S2 state is completely non-emissive, is usually not populated by direct electronic excitation, is very short-lived, and so its emission makes a Minuscule contribution to the steady state intensity usually undergoes rapid intersystem crossing. So there is generally so if suppose this is S1, this is S2, sorry, this is S1, S2, S3, and we have S0. So there is so much energy gap between the S1 and S2. And if somehow we are exciting S3, it will come to S2, then S1, and then emission happens from the S1 state. Okay, so what happens? So there is an energy gap between the S0 and the S1 state so much. So even if we are exciting the S3 or S2 state, they are because of the less energy gap with respect to the S1, there is a relaxation happening, and then they come down to the V0 level of the S1 here of the S1 state, and then emission happens from there. So because the short-lived nature of S2 and S3 states, less energy gap between S3, S2, S1 state, the emission happens from V0 of S1 state. Okay, so to answer this question, the Kausha's rule first of all says that the emission spectra is the mirror image of the absorption spectra, and we get emission from the lowest vibrational level of the S1 state. Okay, lowest vibrational level of the S1 state. So this is the lowest vibrational level and the S1 state. So this is the Kausha's rule, and it is obeyed because of this condition, because these higher excited state, even if we excite, give more energy and excite to S3 and S2 states, for most of the fluorophores they are short-lived, and there is a less energy gap between S2 S1 state or S3 S2 S1 state. So they relax back to S1 V0 of S1 and then emit from there. So to answer this question, the answer is C. Because of the short-lived nature of the higher excited state, the emission makes even if the emission is coming, it will be very minuscule, very nominal in comparison to the emission coming from the S1 state. So it is not seen in the emission spectra. So the answer is C. Okay. And when is Kausha's rule violated? So Kasha's rule said that the absorption and the emission spectra should be mirror images. But when the excited state process happens, it's not mirror image. Due to the excited state process happening, there is a new peak which is redshifted. Okay, so let's move to the next question. And now we move to the plasmonics part. I think the lecture 55 and 56 maybe of the course, and this a few questions are there. We'll finish it fast. So the first question is, the principal relaxation pathways in plasmonic nanoparticles are phonon-phonon coupling, electron-phonon coupling, and electron-electron coupling. The typical time scales of them are respectively. So for electron-electron scattering, it takes hundreds of femtoseconds. Okay, and for electron phonon coupling, it happens between 1 to 4 picoseconds. And the phonon-phonon coupling, it takes place in 100 picosecond. My pen is not writing properly. So the fastest one is this one. So this is the fastest electron-electron scattering. It happens in hundreds of femtosecond. Then first one is phonon-phonon. So phonon-phonon in 100 picosecond. Phonon-phonon 100 picosecond. Then electron-phonon 1 to 4 picosecond. And then electron-electron scattering in hundreds of femtosecond. So the answer will be A. For ninth question, electron phonon relaxation time of cold nanoparticle is same as that of the bulk cold when the pump power is 0. So electron phonon coupling time is 0.65 picosecond, and this one is bulk cold at 0 pump power. When you extrapolate it to 0 pump power, then the electron phonon coupling is same as that of the bulk cold. But when you excite at higher pump power, there is a lot of interactions that can happen, and the electron phonon coupling time at higher pump power increases. And when it increases, the coupling will not be that much good, because the coupling constant, that is the K, is inversely related to the time constant of the coupling, right? So if at 0 pump power, it is same as the bulk. So here the answer will be 0. Okay, let's move to the next question. So with increase in the size of silver nanoparticles, electron scattering time constant increases to saturation, increases monotonically, decreases monotonically, or decreases to saturation. So let's see. Electron coupling in Ag particles. So the graph which comes is like this. So this is the radius of the nanoparticle increasing in this direction, and this is the coupling. So starting with 100, 200, 300. So it and then comes to saturation for other radius. Okay, so it saturates. So for increasing radius, with increase in the size, it increases. With increase in the size, it is increasing, and then it is saturating. So answer to this question will be, it increases to saturation. There is an initial rise because with the increase in radius, there is some equilibration happening, and the energy gets redistributed among all the electrons. Okay. Let's move to the next question. In case of gold aggregates, electron phonon relaxation time is independent of wavelength, decreases with increase in wavelength, increases with increase in wavelength, and first increases, then decreases and with increasing wavelength. So for aggregates, so for AU aggregates, the relaxation time versus radius, so versus wavelength comes like this. This is 520, 580, 640 nanometer, and here is the relaxation time 0.4, 1.2, 2.0. So the graph which comes is like this. Okay, so increase in the electron phonon relaxation time decreases. It's not independent of a wavelength. It decreases with the increase in the wavelength. So here you can see as you go at the longer wavelength, there is a decrease. Electron phonon relaxation time decreases with increase in wavelength. So increase in the electron oscillation and the electron oscillation and the phonon spectral overlap happens, and the interfacial scattering with more aggregation, it leads to faster faster relaxation time. So here the answer will be decreases, the phone relaxation time decreases with the increase in the wavelength. The 12th question is, for two-component alloy nanoparticle of Au and platinum, the relaxation time electron phonon is given by. So the equation which was given was like this. Of Au plus 1 minus alpha Au, where E pH of platinum. So you can take alpha Au tau EPH platinum plus 1 minus alpha Au tau EPH Au divided by tau EPH Au tau EPH platinum, and this is 1 over tau EP electron phonon coupling relaxation time. So on taking the inverse, this term will go up and this term will go down. So I think the options are tau EPH of Au and platinum should be in the numerator. Okay, for all of them it's in the numerator. Let's check the denominator. There should be a plus sign in between, so we can cancel out this. It has a negative sign, so these two are wrong. Plus 1 minus, this is 1 here, so it will be 1 minus alpha Au EPH of platinum. It is given, but it should be Au here, so here it should be Au, so this is also wrong. So we are left with 1 minus alpha Au plus alpha Au and tau EPH of platinum. So answer is this one. So take reciprocal of this. Okay, so answer will be C. So the 13th question is, the variation of electron-phonon coupling time of Au platinum alloy nanoparticle is not linear with its composition because the answer to this is it's not linear because there is a difference in the density of states of Au and platinum. So the variation is not linear. If the variation is like this, if this is Au, it's starting from 0 and this is 1. This is the composition and this is the relaxation time in picosecond. So it's not linear, it goes like this. So this happens because there is a difference in the density of states of Au and platinum. Okay, let's move to the last question. In case of Ag and Au nanoparticle, alloy nanoparticle, electron-phonon resonance time is independent of the composition, goes through a minimum, varies linearly with composition, goes through a maximum. So for Ag-Au alloy, the electron-phonon resonance graph with respect to composition, it looks like this. So for different size, so the graph is here, let me write. This is electron phonon and this is the composition starting from 0 to 1. Okay, so for different diameters the graph is like this, like D1, D2, D3. Okay, for different diameters the graph is linear. For gold and platinum it was not yes, for gold and platinum this is not linear, it was increasing. So this was due to the difference in the density of states of the gold and platinum, but here in this case in gold and silver it is linear because their density of states is similar, that is alpha Au is equal to chi Au, that is density of states of Au is equals to density of states of Ag. So the answer of this question will be that it varies linearly with the composition. It doesn't increase or decrease. Okay, so the answer will be C. Okay, so this finishes, I think, our discussion. Yes, this was the last question. So we have discussed all the 14 questions of the assignment 10, and next week will be maybe a longer session of 3 hours. I will share the link here. Stop presenting first. So I'll share the link of the next week's session. You guys will get the. So next week we have to discuss two assignments, the 11th and the 12th one. So I have increased the time by 1 hour. So next week's session will be the last session. So it will be of 3 hours. So I'm putting the link here. This is for the next week. It will be from evening 6 to 9 p.m. Okay. So I'll end this session now here. I hope you're following all the lectures and the sessions. Thank you.